We're going to look at the last two examples, example 4 and example 5, on the Graphing Rational Functions worksheet, or the notes, I should say. When we look at our next example, notice that unlike the other examples, we have a larger degree in the numerator than we do in the denominator. In this case, I'm going to factor my numerator and then look at my numerator and denominator to find information about the graph. So we have an x minus 2 and an x plus 2 in the denominator, or the numerator, and then an x plus 1 in the denominator. Once again, we have our vertical asymptote is going to be at -1 because y is undefined at -1. So that's the same thing we've been doing. We're also going to be looking at our x-intercepts and y-intercept. So if we put in 0 for x, notice we would end up with 0 squared minus 4 over 0 plus 1, leaving us with -4. So we have the point 0, -4 on our graph. Then if we put, we look at what values would make the numerator equal to 0, so that would make the whole function equal to 0. So in other words, if I have x minus 2 times x plus 2 all over x plus 1 equal to 0, then I really just need to know where are x minus 2 and x plus 2 equal to 0. Because if the numerator is 0, the whole fraction is 0. So x equals 2 and x equal -2 are the x-intercepts. So -2 and +2 are my x-intercepts. That one's a little off for some reason. It doesn't want to go in the right place. There we go. X equals -2 and +2. Now it's time to look for other asymptotes besides vertical asymptotes, or to look at our endpoint behavior. So there we have our vertical asymptote, our intercepts, endpoint behavior. Endpoint behavior when x gets very, very big or very, very small, x goes to plus or minus infinity. So let's think about what happens if we have x squared minus 4 over x plus 1. Basically, we're thinking like, for example, 1,000,000 squared minus 4 over 1,000,000 plus 1. Well, if we keep making x bigger, what's going to happen to y? As x goes to infinity, y is going to go to infinity. It's going to get even bigger. So we don't have any, there's no horizontal asymptote. It doesn't level off to any one number like it has when the degrees are equal in the numerator and denominator, or the denominator has the higher degree. So no horizontal asymptote here. So how do we find an asymptote? So here's the big idea. Big idea here. When the degree in the numerator is greater than the degree in the denominator, then we need to divide the functions. So finish writing here. When degree in the numerator is greater than the degree in the denominator, we divide to find the asymptote. Now that asymptote, if we divide an x squared by an x, we're dividing a quadratic by a linear, we're going to end up with a linear. So we're going to have one of those slant asymptotes. Denominator is x plus 1. And I'm going to be dividing that into x squared minus 4, so x squared plus 0x minus 4. I think it's easier to see when I do long division, so I'm actually going to do long division here. What do I multiply x by to get x squared? I multiply it by x. X times x is x squared, and then x times 1, remember multiplied by both, is x. Subtract, and we end up with -x minus 4. So we multiply by -1. So -1 times x is -x. -1 times 1 is -1. Subtract. -4 minus a -1 gives me -3. So I have a remainder. The way I write this then is that f of x is equal to x minus 1 plus -3 over x plus 1. And now I'm going to ask myself the question again. What happens as x goes to infinity? As x goes to infinity, this particular part of the equation gets very close to 0. So what happens to y? Y starts to look like the equation x minus 1. In other words, y equals x minus 1 is a slant asymptote. So we have a linear asymptote that is not horizontal, so we call that a slant asymptote. So I'm going to graph the line y equals x minus 1. I could plot a couple points, and actually there are already there are pretty close to points on here. Negative 1 would be my y-intercept. My slope is positive 1, so let me just put another point in. If x is 2, y would be 1. If x is 4, y would be 3, and so forth. So plotting a few points, here is my other asymptote. And I'm making a dotted line because this isn't the actual graph, it's an asymptote. So how does the graph behave? Well, you see I have 2 points to the right and below the slant asymptote. So basically, one part of my graph goes along the asymptotes over there. And then I have another, with my other x-intercept, I have to go up here and along the asymptote like this. So that's what the graph looks like. What this tells me is as x goes to infinity, y starts to behave like a line. So basically, I have, except for this violently torn part right in the middle, the graph just looks like this line. So this is a little more easily seen if we look at the graph on the calculator. Here's what the graph looks like, and I'm going to zoom out on this graph. So if I'm going to go to Menu and Window, Zoom out. And it just asked me to pick the center, so I'm going to zoom out with this being my center point. If I zoom out again, notice how the graph basically looks like a line, a diagonal line, but with a little break in the middle. If I zoom out again, it's looking more linear with a little break in the middle. If I do zoom a couple more times, that vertical asymptote's getting so close to the y-axis, and we're zooming so far out that it gets to the point where you really can't see it anymore. It's still there. It's still there because if I were to, I'm going to escape out of this and get into trace mode. If I were to trace this, I'll still find out that if I get really close to -1, the line, my point's not going to just travel along this line the whole time. If I get close to -1, you're going to see this, that there really still is a vertical asymptote here that's going to make the graph go, make the y value go either really large or really small. So if I trace, type in, for example, if I type in -1, first of all, nothing happens. That's kind of interesting right there, because if I typed in 2, for example, I get a value. But if I type in -1, for some reason it doesn't write -1 undefined like it has before. I wish it did, but it doesn't. But what happens if I type in something close to -1, like -1.0001? Notice, look at I'll have to move this out of the way. Look at my y value, 29,998. Okay, clearly has moved up this vertical asymptote because that's nowhere close to where the line was. If I typed in -0.999, oops, why isn't it letting me type in anything? If I type in -0.99999, now look at it's jumping to a really large negative value. Now it's at -3 times 10 to the 5th. So we're at -300,000 it looks like. So notice that we do that break, that unusual thing that happens near the asymptote is still there. It's just that when we look at the graph all zoomed out, we don't see it. So that's what I'm seeing. I'm not seeing what the graph looks like. I'm not seeing that asymptote when I zoom out one more time. I'm just seeing the line basically. Okay, so let's go back here. One more example. This one, if we graph this, I'm going to show you what this looks like graphed on the calculator. I said graph this on your calculator. Are you surprised? So if we look over here, here's the graph. It just looks like a line. I don't see any vertical asymptotes at all, and yet I know that x can't equal 3. If I go through and trace this, and I type in 3 for x, I do get an undefined value. X can't equal 3. So the question, what's happened when x gets close to 3? Because if before when x got close to the undefined value, I had a vertical asymptote, and it was either going to go to positive infinity or negative infinity. It's going to go really big or really small. So let me type in something close to negative 3 and see what I get. So if I type in negative 3.001, close to negative 3, notice that, oh, I'm sorry, positive 3, not negative 3. It's close to positive 3. Positive 3 is my undefined value in the denominator, my mistake. So if I put in 2.9999, look at that, I get negative 1.0001. Let me put in 3.0001. Now I get negative 0.9999. Both points are really close together. Now I don't have one going to positive infinity, one going to negative infinity. They're both getting close to negative 1. Basically what I have here is a hole in the graph. My function just moves along this line, just going along here, and then when I get to 3, there's just no point there, and then I keep going. You can't see the hole in the graph on the Inspire, even if you zoom in. I've tried it, but it's there. There's a non-existent value right there at 3. So how do we handle this algebraically? Well, let's go ahead and factor the numerator. When we factor the numerator, we find out why this happens. When we factor the numerator, we find out that there is a factor in the numerator that matches the factor in the denominator. In other words, if I were to plug 3 into the function, I'd get 0 in the numerator and I'd get 0 in the denominator. So instead of having a 0 in the numerator, meaning, oh, that's an x-intercept, and a 0 in the denominator, meaning that's a vertical asymptote, we get neither. So here's the issue. If 3 makes both the numerator and the denominator equal 0, the numerator and the denominator, wish I could just instantaneously write this for you, equals 0, then it is neither a vertical asymptote nor an x-intercept. Okay? If 3 makes both the numerator and the denominator equal 0, then it is neither a vertical asymptote nor an x-intercept. It is a hole. Okay? So how do we figure out how to graph this? If we look at the numerator, let's go ahead and do x and y intercepts. We don't have any vertical asymptotes. So x-intercepts are when the numerator equals 0. 3 doesn't count, but I still have 4. X equals 4 is an x-intercept. Y-intercept, I can still plug 0 into the function, and I get f of 0 gives me 12 over negative 3, which is negative 4. So negative 4 is a y-intercept. So I know those 2 points. Now, how do I figure out what the graph does? Well, because the degree in the numerator is larger than the degree in the denominator, I divide the function. So if I divide x minus 3 into x squared minus 7x plus 12, let me zoom, kind of scoot this up just a little bit. This goes in x times, I get x squared minus 3x. Subtract that from negative 7, and I get negative 4 because it's negative 7 minus the negative 3 plus 12. Then I have to multiply x times negative 4, and I get negative 4x plus 12 because negative 3 times negative 4. Subtract that, and I have a remainder of 0. So when I have a 0 remainder, it means I don't have an asymptote. So remainder, get this kind of out of the way. So remainder equals 0 means the graph is the line, not as close to, but it is the line y equals x minus 4 with a hole at the point 3 comma negative 1. Now where did I get the negative 1 from? Well, if I plug 3 in for x, y equals 3 minus 4 is negative 1. That's where I got this negative 1. So basically I have this line, but I can't use 3 as a point on the line because in the original function, before I divided, x couldn't equal 3. Another way you can just look at this is these two just can cancel out. And so this is equivalent to the line y equals x minus 4, except for I can't have 3 as a point. I can't have the value when x is 3. So when x is 3, which is right here, there's a hole in the graph. So I just draw a circle, an open circle, to indicate there's a hole in the graph right here at the point 3, negative 1. And other than that, the graph is just a line. Now let's summarize what we've done so far. There's on the separate handout, which I've given people, I've summarized here basically what's the definition of a rational function. It's a polynomial divided by a polynomial. How to graph rational functions. We find all the zeros of the numerators and the denominators of the numerator and the denominator, and then do these things. If a number is a 0 of the denominator only, it's a vertical asymptote. If it's a 0 of both the numerator and the denominator, we have a hole. Both of these things are called discontinuities because they're gaps in the graph. We've done x and y intercepts. This is just a summary of how to find x and y intercepts. Once again, if a number is a 0 of both the numerator and the denominator, it does not count as an x-intercept. It's a hole. Endpoint behavior. We've looked at several different examples of endpoint behavior, but they all fall into 3 categories. Category 1 is when the degree of the numerator is less than the degree of the denominator. When that happens, there will always be a horizontal asymptote at y equals 0 because the denominator is getting bigger at a much faster rate than the numerator, and it's getting close to 0. If the degree and of the numerator and the denominator are equal, then we still look at the leading degree or the highest degree terms in both the numerator and the denominator. But in this case, imagine putting a million. You'd have 3 times a million squared and over a million squared. Minus a million, minus 3, minus 8 million, minus 5. Believe it or not, the 3 times 1 million squared is so much bigger than the million that these last 2 terms are actually not going to make much difference as x gets really, really big. When x gets infinitely big, these other smaller terms are not going to have much of an effect at all, and it's just going to level off to 3. So there is a horizontal asymptote not at 0, but at another number, the number determined by the coefficients of the numerator and denominator's largest degree terms. Then the third case is when the degree of the numerator is larger. If the degree of the numerator is larger, there is no horizontal asymptote. You divide the numerator by the denominator. If there's a remainder, then you have a slant asymptote. If there's no remainder, then you just have that being your line with a hole in it, or that being a line or a graph, whatever it is. It could be, if this were x cubed over x, you could actually have a graph that looks like a parabola, except for either a hole or a vertical asymptote in it. And then down here just talks about what we did, reminding when you can cross an asymptote, when you can't, how you figure out what the rest of the graph looks like after you found those key points. So this is just summarizing all the things we talked about in the examples. That is the end. In your homework, then make sure that you can do these graphs without using your calculator, but then use your calculator to make sure that your answers were correct. But on the test, you will have to do some of these graphs without a calculator, so that's what you want to practice on.